Hello. Today I will be reviewing two topics that I think are likely to be on the AP Calculus exam. They will be finding limits algebraically and continuity. Topic 1. Finding limits algebraically. The first thing to know about finding limits algebraically is the direct substitution property. This states that if f is a polynomial, rational, or algebraic function, and if a is in the domain of f, then the limit as x approaches a of f of x is f of a. It's important to note that you can use direct substitution to find the limit of any polynomial as long as the limit is within the function's domain. Now here's an example of the direct substitution property. The limit as x approaches 3 of x squared minus x plus 3 over 5x squared. All we have to do is plug in 3 for x and simplify. But what if the denominator equals 0? A function is said to be indeterminate at x equals c if f of c is undefined. Examples of undefined values could include anything divided by 0, infinity divided by infinity, infinity minus 0, or infinity minus infinity. Indeterminate limits could be found through graphs or tables, but also algebraically by manipulating the function so the denominator is no longer 0. Here's a quick example of solving an indeterminate algebraically. Notice that if we use the direct substitution property and plug in 0 for x, we end up with 0 over 0, which is indeterminate. Instead, we have to factor out the x squared. The x squareds cancel out, and we are left with 5x squared plus 8 divided by 3x squared minus 16, which, when 0 is substituted in and it is simplified, equals negative 1/2. Another important part to finding limits algebraically is the squeeze theorem, which is also known as the pinching or sandwich theorem. All these numbers and variables are a fancy way of saying that if one function is squeezed in between two other functions, a higher function and a lower function, and these functions have the same limit as x approaches a certain point, this middle function that is squeezed in between the two will also have the same limit at that point. Trigonometric limits can also be found algebraically. Here are two important trig limits to memorize for the AP exam. First of all, the limit as theta approaches 0 of sine of theta divided by theta is always 1. The limit as theta approaches 0 of 1 minus the cosine of theta divided by theta is always 0. An example of finding the limit of a trigonometric function is the limit as x approaches 0 of the tangent of theta divided by theta. We use a trig identity here to find that the tangent of theta is equal to sine of theta divided by cosine of theta, which would then help us simplify the limit into the sine of theta divided by theta times 1 over the cosine of theta. We know the sine of theta divided by theta is 1, and we can use the direct substitution property to find the limit of 1 divided by the cosine of theta. We end up with 1 times 1, which equals 1. Finally, here's a list of some basic limits that might be helpful to finding limits algebraically. Remember, these are only true if a is in the domain of the function. Topic 2. Continuity. This definition in green helps determine whether or not a limit exists, which further can help us determine whether a function is continuous at point C or not. A function is said to be continuous at x equals c when it meets 3 criteria. First of all, f of c must exist, so c is in the domain. The limit as x approaches c of f of x must exist, and this limit as x approaches c of f of x must equal f of c. So we know a function is continuous when it is defined at every point along its domain. But what about functions that are discontinuous? Such functions can be divided into two subcategories. First is removable discontinuity, and an example of this would be a hole in a graph. And next is non-removable discontinuity, which includes things like jumps or oscillations. Step functions are a classic example of non-removable discontinuity because they have jumps between values. Some important limits to remember for step functions when n is an integer is that the limit as x approaches n from the left is always equal to n minus 1. The limit as x approaches n from the right is always equal to n. What if we have a number that is a non-integer? We would call this a and say that a lies between n and n plus 1. The basic limits to remember for non-integers are that as x approaches a from the left side, the limit is always n, and as x approaches a from the right side, the limit is also n. Now let's do a practice problem involving continuity. We need to find if this piecewise function is continuous at x equals 1. This is a pretty easy limit to find because we can find the limit as x approaches 1 from both the left and the right using direct substitution. And both times we will get 9 as our answer, which means that the limit does exist. But just because a limit exists doesn't necessarily mean a function is continuous at that point. However, we do know that this function is continuous at x equals 1 because, first of all, we know that x equals 1 is in the domain. You can plug 1 into both parts of these piecewise function and get an answer. And also, this answer that you get is 9, which is the same as the limit as x approaches 1 for both sides. So we can say that f of x is continuous at x equals 1. The end of Module 1 review.